All right, we got about 5 seconds to go, and I just got my coffee, and that's why I quoted that StarCraft line, which is jacked up and good to go. I think that was the Marines. I don't know how many of you played StarCraft. I never played StarCraft 2, nor the expansion pack. Just the first one when it first came out. That was fun. All right, so let's go ahead and get started. This is an overview of what we'll be talking about today. We actually talked about these 4 instructions yesterday. Increment, jump I. So there's an I after the JMP, so that's kind of important. There's also CMP, which is compare, and JCI, which is a very interesting instruction because it's a conditional branch instruction. Depending on the carry flag, which is also the borrow flag, it will either jump or not jump. Okay, so JCI is one of the more interesting instructions because it is used to implement conditional branches, which basically forms the basis of a lot of control structures that we see in C, C++, and just about any programming languages. We do not have a single instruction to do loops, or there's no single instruction to do many of the things that we take for granted in a high level programming language. So we only got a few really simple conditional branches, but by combining these instructions with other instructions, we can do a lot of complex control structures, just like any high level programming language in assembly. We'll also, since we just talked about JCI, we'll also talk about how the flags are actually maintained and how they are determined in the processor. They're mostly done by the ALU, but there's one component outside of the ALU that's responsible for the flags. We'll go through these instructions step by step, like transition by transition today. So this is one more review, for those of you who want to get a little bit more exposure to how the processor works. I got some questions, regarding the output of the ROM, how it splits into the various tunnels that we use to control the multiplexers, demultiplexers, the registers, and also RAM. So we'll talk about that a little bit. And depending on whether we have enough time or not, we'll go ahead and I'll show you the tool that I use to create the ROM content, because it's really quite obvious that someone like me would not be doing that by hand, because it's really kind of like chewing styrofoam. It's not exactly something I would like to do. All right. So let's go ahead and get started. So we'll go ahead and get started with, I'm looking at the 4 instructions here, and I'm just trying to decide which one that I want to go for first. So let's go ahead and start with maybe increment. So we'll start with increment first, because it is interesting in its own way. Even though it doesn't sound very interesting, it is actually one of the more interesting instructions. So we go to the opcode table first to look up how it is described, and also how we can determine the opcode for increment. So we look it up, and it's one of the later instructions. So here's increment X on row 36, and I'm just going to pin this tab so that it doesn't refresh, because that can get a little annoying after a while. So let me do that. Right click, auto tab discard, and we'll say keep this tab for this session so it doesn't automatically get rid of it. Uh-oh, no sound? Did I mute myself? Okay, so let me check first, because I turned off certain things in Discord, so I'm going to turn it back on. Oh, I see why. Because it's the threshold. Oh, nope, that's not it. Okay, I'm going to turn that on. Is that okay now? Can you guys hear me at this point? Oh, okay. Yeah, so the one setting, so this is good for people to know too. So what I did this morning was I tweaked things, probably unnecessarily, but that's kind of what I do usually. Was that I changed the input sensitivity of the audio or the voice settings, and I turned off automatically determine input sensitivity, thinking that the default setting is probably good. As it turns out, that is not the case. I still have automatic gain control turned off, so if the audio doesn't seem as good as yesterday, just let me know and I will turn automatic gain control back on. All right, cool. Thank you. Thank you for letting me know that the voice is missing. YouTube is different because YouTube gets the voice directly from the audio driver and not from the same setting as in Discord. So it is possible that I miss, that the voice doesn't appear on one or the other side or both. Um, but because that's because they are independent settings. So that's good to know. Okay, very good. So getting back to today's lecture, what we'll do is we are going to talk about the increment instruction first. So the increment instruction starts with a prefix of 1101, and then you can see that it doesn't have XXYY. The YY is missing because we are only incrementing one single register. So now the question is, okay, this is the interesting question, is if you look at this particular bit pattern and you look at this particular bit pattern for OR, you can see that they are almost the same. Okay, they both start with 1101 in binary, but because OR requires two operands, it has XXYY because it needs two registers, and increment only has XXXX, which because when you're incrementing, you're only incrementing the value of one single register and not two registers. So now the big question is, if I specify 1101, okay, which is the fixed bit pattern of the opcode, and then we specify 0000, what is it going to do? Is it going to perform an OR operation, of register A with register A, or is it going to increment? Okay, so that's a good question, okay, because it does, from the opcode table, it doesn't tell you which one it is going to be the one corresponding to the opcode of 11010000. So why don't we just play with this and determine, okay, using the emulator, using the simulator, we'll decide. The space is really just there to separate, because otherwise it would look like XXXX, XXXX, right? That's it. So I put a space over here just to, kind of as a visual spacer to separate, the four X's, so that we have, XX being one group and then XX being the other group. Because it's basically the pattern of XX repeating itself. Is that answering the question? That is correct. We do not, well, in fact, we don't type this space either. The space between the 1101 and the first pair of XX, that space is also just visual, just so that we can separate different components of the 8-bit opcode. Okay, so now let's go ahead and play with the simulator, okay? Because I want you guys to play with the simulator as well, to experiment, to try out different instructions, because that is how we get familiarized with the processor design. So the first thing I do is I'm going to do a reset, Control R, resets the entire thing, including RAM. Then we go back to the RAM component and we just put in that code. It's 1101, which is a D, and then a 0. Okay, so this is D0, which can be OR AA, or it can be increment A. So we want to find out what this one does. Okay, so what we'll do, because it's the beginning or the first thing of the day, so what we'll do today, is we'll go ahead and execute the instruction, really step by step. But before we do that, okay, we'll go for something that's even more important, more fundamental, which is looking at the output of ROM. In this case, it is 1080007. And if you poke the wire you will see exactly the same thing. See how you can see 1080007. Now remember, I changed the radix or the base of of the display to hexadecimal. So if you don't change it, it's going to display a pretty big um, base 10 number. Okay, but because I did change mine, that's why it displays 1080007 in hexadecimal, but it also displays the binary equivalence of that hexadecimal number. And you can probably see that the translation is 100% correct. The 01 corresponds to the 1, the 0000 corresponds to the 0, 1000 corresponds to the 8, a whole bunch of zeros over here, and then 0111 corresponds to the 7. Okay, so everything does work out. So now the question is, how does it split into the individual bits to control all the components inside the processor? So we can see that some of these do not have a name. Okay, like bit 25 doesn't have a name. All it does is to go into the OR gate and then go into the reset or the clear or the 0 of of the microcode pointer. So and bit 25 is usually off because the moment it is on, the moment it turns into 1, the microcode pointer goes back to location 0. Okay, so we don't need it very often. Bit 24, which is this Y here, is also does not have a name. I don't give it a name, because it goes really kind of locally back to the select of this particular multiplexer. So I don't give it a name because there's no need to make a tunnel out of something like this. Now the more important part is microcode data. Okay, so this, if you look very closely, okay, we can zoom in and look look it up. So you can see how it is this one single wire coming out of a splitter actually has 21 bits in it, okay, because it's corresponding to bit 3 to bit 23 of the output of ROM. And that goes into its own little, well, I shouldn't say little, but it goes into its own splitter. So I'm trying to see, okay, this is good. I can display both at the same time. So bit 3 over here is actually bit 0 over here. Bit 4 over here is bit 1 over here. So in other words, if you want to look at microcode data and figure out which bit over here is corresponding to which bit of the ROM, but not the first splitter, the output of the first splitter, then you have to add an offset of 3 to all of these numbers. So I'll just randomly pick one. Okay, let's pick this one over here. So if you want to figure out what bits in the ROM, okay, for each location in ROM corresponds to register output 0 demultiplexer, it's not going to be bit 8 to bit 9, excuse me, it's not going to be bit 7 to bit 8. It's going to be 7 plus 3, which is bit 10, to 8 plus 3, which is 11 of the ROM. And then Catherine asked, isn't every first bit coming out of ROM a 0? Okay, so let's check that. Okay, so every bit coming out of ROM is not a 0 because that's a 1, that's a 1, that's a 1, that's a 1, that's a 0. Not every, very. Oh, the first bit, which is this one, because this is bit 0 of the output of ROM, and it certainly is not a 0 in this case. And let's see where it connects to. This one also does not have a name because I can connect it locally. So this one goes to the enable of the instruction register. The member in the yellow box was a 0. Okay, so let's check that. So we'll click here and see whether bit 0 is a 0. Nope, that's not a 0, that's a 1. So I think Catherine is looking at this 0 here, which is bit 25. Ah, okay. Yeah, so this one, the one where my mouse pointer is located is bit 25. It is the most significant bit. This one over here is bit 0. It is the least significant bit. Okay, all right, that's cool, no problem. All right, so this is how we count the bits and determine which bits go to which particular tunnel. And obviously, even if I know exactly how to set all of these tunnels to re-stitch everything into the hexadecimal number in ROM, takes a little bit of work. Okay, it's really just chore, just bit shifting a whole lot of stuff to reconstruct the 26 bits that we need to store in the ROM, and then convert that into hexadecimal, because the ROM content is all specified in hexadecimal. the black wires are not zeros. Okay, Catherine was asking whether the black wires are zeros or not. So we got 3 different colors here. We got light green saying is a 1. Yeah, that's right. That is correct, Catherine. The black wires are basically saying that there are multiple bits inside, and therefore it cannot be color coded to indicate whether it's a 0 or 1, because it has a whole bunch of wires, so they cannot be, so as a bundle of wires they cannot be color coded, and that's why Logisim uses black as a color instead of light green or dark green, because you cannot just look at the color to determine the states of the individual bits of a bundle of bits. So that's also correct. All right, so let's zoom back out. Okay, so that discussion a little bit earlier, was basically telling you guys, how we take the output of ROM and be able to split it into all of these tunnels and some of the wires without, tunnel names, so that so basically the entire configuration of the processor of all the components is determined by the output of the ROM. Okay, so everything originates from the ROM itself. Okay. So now we have the fetch cycle. The fetch cycle really refers to the rising edge event when the microcode pointer is at location 0, 0, 0. Okay, because this is when we fetch the opcode. So when we do a Control T, we can see how the opcode is now fetched into the instruction register over here. And then the falling edge of the processor, when microcode pointer is 0, 0, 0, doesn't do much. Okay, all it does is to increment the microcode pointer so that we get to location 0, 0, 1 in ROM. So here we go, your Control T. So now that we are at now that we are at location 0, 0, 1 of ROM, the rising edge itself doesn't do much. Okay, all it does is to increment the program counter so that we are preparing ourselves for the next fetch operation. So this is where the program counter is. So when I Control T again, the program counter would increment from 0, 0 to 0, 1. Okay, Control T, there we go. The falling edge when microcode pointer is 0, 0, 1, that is important. Okay, that is the decode cycle when we execute an instruction, and that is when we copy the entire instruction register, which is now D0, into the most significant 8 bits of microcode pointer, and then just put zeros into the least significant 4 bits of the microcode pointer. That is the decode process. Now, if somebody is to ask me, does every single processor do decode and fetch like this? The answer is no. Okay, but the function of those individual cycles is still the same. Okay, the decode cycle is basically looking at the instruction, the opcode itself, and then determine, okay, now what do I do to configure all the individual components of the processor? That is the decode cycle. In this particular design, which is a very simplistic design, I just use okay, let me Control T again to show you what I mean by that. So I use the opcode, with a 0, appended to the lower end, and I use that to determine which location of ROM, is going to output all the bits that I need in order to configure all the components of the processor to do what the opcode is supposed to do. So this is what I call the implementation of an instruction, okay, which is basically asking how do we configure all the multiplexers, all the demultiplexers, all the registers, and RAM itself so that the processor as a whole is going to perform the function that the instruction needs to do. And in this case, the instruction is unknown, okay, because we are trying to determine, are we doing a OR operation or are we going to do an increment operation? Because it is not clear from the opcode table which one it is going to be. So now we need to go to the various components. So I always start with RAM, okay, but that's just me. You guys can have your own list to go through. So I start with RAM and I look at RAM select here and go like, RAM is not utilized in this case. So that saves me a whole bunch of questions, right? Because if RAM is not selected, I don't even need to know whether RAM load is a 0 or 1, or who is driving the address port and or who is using the data port, because RAM is not used, okay? It is dozing off for this particular cycle. Okay, ignore that. So now we go to the other components, okay? We see some green wires, light green wires. So those are all usually indicative that something is being used, okay? Unless it's connected to a constant like this one over here, then obviously it's always going to be a light green wire, okay? It's not going to be indicative of anything that is particularly important. So we look at the register bank, okay? The register bank has input enable being a 1, which means, yeah, we are updating one of the registers. But increment would update a register because it's incrementing a register, and the OR operation would also influence or change the first of the two registers. So this by itself does not really quite tell us what the operation really is. We can also see that register output 0 enable is a 1, which means this wire coming out of the register bank is connected to, okay, based on this select over here, it's connected to this wire, which then goes into the ALU. This is the ALU, or the arithmetic and logic unit. So we go like, okay, does that tell us what kind of operation we are performing? The answer is no, because increment, which is adding 1 to a register, needs the ALU because it's an arithmetic operation. The OR is also going to use the ALU because it is a logical operation. So both of those operations will need to use the ALU. So that's why when you see the ALU itself is enabled, that also doesn't tell us whether it's an OR or a increment operation. Okay. So maybe if we look at the cell, this ALUOP here, which selects what operation we want to perform in the ALU, maybe that will tell us something. And we can see that it is a 0, 0, 0. But what does that mean? Okay, what does it mean when the ALU operation is 0, 0, 0? Now that corresponds to SEL or select, or operation select of the ALU. So when we go into the ALU, now we want to track it down, okay? So we can see it has 2 input pins, 2 gigantic input pins. We'll ignore that for now, but instead we'll look at operation select, which is ALUOP at this point. And I accidentally clicked on one of the bits, and that's why it prompted me, do you want to create a new instance? Because but my intention was not to change the configuration of operation select. My intention was only to select it so that you can see which input pin I was poking on. So now we look at this wire and go like, okay, how does this input pin, okay, which we know as ALUOP from outside of the ALU, how is that configuring the ALU for the operation? we can see how it is the select of both of these demultiplexers. So when the select of a demultiplexer is 0, 0, 0, that simply means the input is connected to output 0 right there. And same thing with this one, it is only connected to output 0. So now we know in 1 and in 2, okay, once again I poked the wrong place. So once again, it is telling us that in1 and in2 as input pins, they are both connected through the to the multiplexers here to the adder. This is our adder. So this is input 1 and this is input 2 and this is the adder performing an addition operation. So now we think about this a little bit and ask, well, is it going to increment or is it going to do OR? Well, the answer is pretty obvious, right? Because both inputs are sent to the adder and not going to the OR gate. This is the OR gate down here. But the demultiplexers are not sending the input to the OR gate here. Then you might say, well, but which output of all of these operations become the actual output of the ALU, right? Because that is also important. So now we look at the output of the adder. It is going into input 0 of the multiplexer that connects one of the 6 inputs to the output of the ALU. So now we say, but how do we select which input of this multiplexer connects to the output pin? It's the select port over here, and we can see how that select port is also connected to OP selection, operation selection, which is the same thing, to going into the demultiplexers over here. It's also 0, 0, 0. So that means the multiplexer is also taking input 0 to connect to its output. So now it's pretty conclusive that we are performing an addition operation and not an OR operation. Because if it was an OR operation, then we would have taken this wire coming out of this OR gate, going into the input of the MUX, and use that as the output of the ALU itself. And that would be corresponding to which operation? This is 0, this is 1, 2. Okay, so if you just hover over this pin or this port, it tells us it is input 5, which will basically mean that when OPSEL is 1, 0, 1, then it would make it an OR operation. But right now, guess what? It's not an OR operation, it is an add operation. Okay, so if it's an add operation, then why are we just adding 1? I haven't really loaded any one of the registers to be a 1, so where is that 1 coming from? We know where that 0, 0, 0 is coming from because we configure the register bank so that register A is going to the output 0, which then go through this demultiplexer and it connects to input 1 of the ALU. So we know where that 0, 0 is coming from as input 1. But what about input 2? Why is it 0, 1? Because I don't have a register that has the content of 0, 1. So that 0, 1 is actually coming from this 0, 1 constant over here. So this 0, 1 is going through this multiplexer and become the output of the multiplexer going in as in2 of the ALU. But that means the multiplexer has to select input, this is input 1, and that this Y here is the is connected to the select of this multiplexer. And all we can see here is it's coming from FC as a tunnel. So the definition of FC is up here. It is the NAND of register output 1 demultiplexer and ALUEN. And we can see ALUEN is a 1 in this case, but register output 1 demux is a 0 in this case. If at least one input of a NAND gate is a 0, the output is a 1, and that's why FC is a 1. So FC being a 1 has two importance, has two significances. Okay. The first one is it connects to the select of this multiplexer. In other words, FC helps the ALU to choose, is it going to use a constant of 0, 1 as one of its input, going to into, or is it going to use register output 1 from the register bank as the to connect to into. So that's the first job of FC, is to help select the source going into. The second importance of the FC tunnel it is that it goes through a NOT gate and it connects to the enable of the flags register. So in this particular case, even though the flags register connects to flags out coming out of the ALU, it's not going to change because the flags register is not enabled, so it's not going to update, based on the content of the wire that I have just selected. So that means the increment instruction does not alter the state of the flags register at all, okay? Which is by design, because when we use the increment instruction, we're typically doing something that we do not want to change the flags register. We are not comparing. We are not trying to figure out whether it's overflowing or whether we are running out of values, for the register. We are just adding one to a register. So this is the increment operation. And once again, we look at in1, it is 0, 0. We look at in2, it is 0, 1. We look at the output of the ALU, it is 0, 1, which makes sense because 0 plus 1 is 1. So now we look at where it connects to. This is a really easy connection because it doesn't go anywhere else. Okay, the output of the ALU only connects to the multiplexer to go back into the register bank. So this particular multiplexer has the select being RIMUX, or register input multiplexer, and it is a 1, which means out of input 0 and output input 1, we're using input 1, which is the output of the ALU. That is going to be the output of this multiplexer going into the register bank. And register input select, which basically tells us which register inside the register bank we want to update, is 0, 0, which means register A is the one that's going to be updated. So it is more clear over here that register input select is 0, 0. So that's why register A is the one that is enabled being a 1, and because the register input itself, which is an 8-bit pin, is 0, 1, and that's why register A is going to update to 0, 1 when I have a rising edge. So if I type Control T on the keyboard right now, you can see how register A is now updated to 0, 1. So that's how the increment instruction works. Now, if I do, let's go back out to main. So if I type Control T again, the next transition is a following edge. The following edge, in this case, will increment the microcode pointer, so it goes to the next location. The next location is 2 followed by all zeros. No, unfortunately, there's no way to take backwards, which is also why a trace sometimes is useful, because you can at least look at a trace and find out what was it like before the transition. But there's no way to take backwards. But I do have one recommendation, based on Catherine's question. I do have one recommendation. You guys can all use a screen recorder when you are experimenting or doing your lab, because that's really just an easy way for you to kind of be able to trace backwards and ask, okay, what was the state of blah 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 before I type Control D accidentally. Screen recording the entire lab session when you are doing the lab was not practical when computer hard drives only have 10 megabytes as its full capacity. Okay, now we are talking about back in the mid or earlier 80s, okay, when hard drives are relatively small. Okay, they only have a capacity of 10 megabytes. Okay, not even gigabytes. We are now talking about terabytes, right? But now these days, you can directly stream your screen recording to YouTube, which is what I'm doing. And since you have like a 2 or 3 terabyte hard drive, on your computer, screen recording something that's up to an hour or even 2 or even 3, it's a drop in the bucket. Okay, after the session, after you do your lab, you go like, well, this went really smoothly. I have no need to keep this video. Then go ahead and delete it. Okay. On the other hand, if you did something and you have saying, oh man, I just forgot what I just did, and the processor is now going into this particular state, then you can use the screen recording, to help you figure out what you did in the process. So I know I'm not just answering, Catherine's question of is there a way to take backwards, because that's just a simple no, but I'm telling you guys, mechanisms that you can use not only for this class, but also for your other classes when you're programming in C, C++, when you're doing something where you might say, I might need to keep a log of all of this stuff here, just in case I did something and I need to go, quote unquote, go backwards to figure out what I just did. Just do a screen recording, okay? With voice or without voice. If you want to annotate what you're doing along the way, that's fine. If not, it's just gonna be the video. So try to use your computers, to the fullest extent, because that's why you got that 2 to 3 terabyte hard drive. It's not for storing all the movies, okay? Who wants to store a movie on a computer these days? I mean, I don't understand that. All right, cool. Do we have any other questions at this point about the increment instruction? It would appear that we do not have a question about the increment instruction. So what we'll do next is to look at the compare instruction. So we are looking at these instructions just one by one. Let me pull my little notes, little post-it back in here. So we are done with increment. Now we're going to look at compare. CMP is compare. So compare is not really particularly interesting on its own, okay, because it is actually less complex in some way compared to the increment instruction. So let's go ahead and try to hand assemble one. So we go to the, oh, nope, this is the wrong tab. We go to the opcode table. And this time we are looking up CMP or compare. And here is compare. So when you look at compare and you look at one of its buddies, which is subtract, you look at these two. Okay, let me highlight these two. And you look at the C notation, which is on column C, which that's coincidental that column C is the C notation. So when you look at the C notation, you look at these two and look at and ask, they're both subtractions. What is the difference? One stores the result of the subtraction back into X, and the other one does not. That is the only difference between subtract and compare. They're both subtractions. One stores the results and the result of the subtraction. In other words, the difference is stored into X, whatever the placeholder X is, which is a register, and the other one, which is compare, does not store the result back. Then it's like, why do we go through this trouble? Okay, if you're subtracting and you're not storing the difference, to some place in the C program, this would not make sense at all. Okay, let me just click on the cell here. So this operation, if you see this in a C or C++ program, it is legitimate, it is legal, it is syntactically correct, but it is senseless. Okay, because you're performing an operation, but you're tossing away the result of the operation. That's because in a high-level programming language, you do not have access to the flags. You cannot utilize the flags in a subtraction explicitly after the operation itself. But in assembly, we can. Okay? So what we want to do is to look at the bit pattern. It is a 1110, which is an E, and then XX, and then YY. Okay, so now we are going to hand assemble a particular compare instruction. Okay, so I'm going to pull this one back in just so that we can document what compare we're dealing with. So let's just say that we want to compare, I don't know, let's see, BC. Okay, we're comparing register B to register C. So now we want to figure out the opcode, the binary opcode to this. So it's going to be 1110. Okay, that part is fixed. Then we have to specify XX. Register B has a bit pattern of 0, 1. Okay, and then register B is 0, 1, and then register C is 1, 0. So when you look at this as a bit pattern, it is now 1110, which is an E, and then 0110, which is a 6. So E6 is the opcode in hexadecimal, and we can just plug this into Logisim and run it and find out what it does. Okay, so just remember E6. Now we switch back to Logisim, do a Control R to reset the entire simulator and go to the RAM component, okay, which is here. And all I need is just to change one single location. Okay, so execution always starts with location 00. So this is the only location that I need to change. And it is E6 that I want at this location. But then I'll be comparing 00 to 00, which is not very interesting. So let's make it more interesting. Okay, so let's go ahead and go to the register bank and go to register B, which is the minuend, and then go to register C, which is our subtrahend, to specify what values we want to use in the subtraction. So we'll go ahead and specify, let's put a 08 over here, and we'll specify, let's do something even more fun over here. Let's do an 80 over here. Okay, so this doesn't look like a whole lot of fun, right? Because we are just using 08 and 80 as the two values for the subtraction. We are subtracting 80 as a bit pattern from 08 as a bit pattern. And I know somebody is asking, even though that person or those people are not typing in Discord, and I know someone is already asking in their minds, which I think is a good thing, and ask, what exactly are the values that we are subtracting? Are we subtracting 128 from 8, or are we subtracting negative 128 from 8? Because one is the unsigned interpretation of 80 as a bit pattern, and the other one is the signed interpretation of 80 as a bit pattern. Well, okay, so now I have to kind of go back in time and ask, do you guys remember there was one time I said, why do you care? And I'm going to ask you again, why do you care? Because the subtractor does not care. Okay, the subtractor just performs all of those operations. And I know exam 1 was a while back, and I did finish all the grading. I just need to write the script to send you the results. Because I don't want to give you just give you an aggregate score for the entire exam. I want you guys to know why you're getting that score. So I'm still finishing the script to send you the detailed breakdown of the points. Okay, but the points are already done. Okay, the part where I have to do the grading part, that part is already done. I just need to have a way to send you the results, because it's in a spreadsheet, and I don't want everybody to see how everybody else are getting their scores. So I need to make it kind of individualized. So anyway, getting back to here. So now the question is, why do we not care? Because the subtractor does not care. The subtractor is only using exclusive OR and not, let's see, what else does it use? There's an OR, exclusive OR, and OR. Okay, so there's an and, there are ORs as well, and there are negations because it's a subtraction. But the bottom line is it's only using logic gates. Okay, logic gates are dealing with zeros and ones. They're only dealing with true and false. They're not dealing with actual values. So the subtractor does not care about the interpretation of the bit patterns. All it sees are zeros and ones. Okay, so that's why I'm not going to tell you, are we subtracting 128 or negative 128 from 8? We are not interpreting the bit patterns into the values. Okay, so of course the next question is, when do we care? And we'll get to that part. Okay, so what we'll do now is single clock. Okay, this is the fetch cycle. What did I do? Okay, Control T. There we go. I type Control Y instead of Control T on the keyboard. So the instruction register now has E6. Control T again. The microcode pointer increments to 001. Control T again. Increments the program counter. And then Control T again. We are decoding to location E60, which is compare register B to register C. Basically, it is just subtracting register C from register B. So without going through every single component to find out what it does, this time we'll just go straight to the ALU and we see the in one is the 08, which is the content of register B. In 2, on the other hand, is 80, which is the content of register C. So how things are routed into the ALU this way, I'm not even going to describe it now because it's going to be the same process as what we did earlier. Okay, and we can see the output of the ALU is going back into this multiplexer, even though the select of this multiplexer is specifying a 1 here. We can see the input enable of the register bank is turned off. So even though the data is presented here and even presented over here, none of the 4 registers inside the register bank is going to update. Okay, nobody is going to update. So now the focus in is what is going on inside the ALU. Okay, how do we determine all the flags and all that stuff? Okay, the first thing is we can now see that the OPSEL, which is known as ALUOP, ALU operation from outside of the ALU, is a 001. So that means these two demultiplexers and this multiplexer and also the other multiplexer down here, they are all selecting input 1 to become the output, okay, instead of 0. So now we look at the output 1, we look at output 1, and oh, okay, they both connect to this subtractor. So the subtractor looks exactly like an adder, except instead of a carry in, it has a borrow in. Instead of a carry out, it has a borrow out. And instead of sending out the sum, it is sending out the difference. Other than that, it works the same way as an adder. Okay, so we can see the first input into the subtractor is 08. We can see the second input into the subtractor is 80. So now we perform the binary subtraction. All right, so this may not be a bad time to kind of remind you guys how to do binary subtraction. How many people still remember how to do binary subtraction? And I see no response whatsoever. Okay, thank you, Catherine. So there's one response saying that yes, we still remember. All right, so let's go ahead and do this. Okay, so 0 0 0 0 1 0 0 0, that's the 808, and we have 1 0 1 followed by all zeros. That's our 80, and we're performing a subtraction. And we are working on this one, kind of sequentially. So this would be a 1 and then a bunch of zeros, 1 and then a bunch of zeros over here, because this is the Q row, which is just the exclusive OR between the X and the Y. And now we have the borrow, okay, or the T row over here. So we have a bunch of zeros over here, and then we got a 1 over here, and that will propagate the carry all the way to here, or the borrow all the way over here, because nope, I made a mistake, sorry about that. These are still zeros, because 1 minus 0 is a 0 is a 1 without a borrow. 1 minus 1 is also a 0 without a borrow. So we don't have a borrow until the very end over here as an overall borrow. Okay, yep, that's right. Catherine caught it too, good job. And then we got the final this is the difference, which is just the exclusive OR between the bits. And we can see that, I think I messed up somewhere. Yep, this 0 is not supposed to be here. There we go. Okay, so let me double check. The first 0 in T, shouldn't the most significant bit of T be 0? No, because we got this 0 minus 1 over here. Oh, you guys are talking about this one. Yes, that one is supposed to be a 0. Good catch. And that one is supposed to be a 1. Now we got it. Okay. All right, so this is the correct result of the, well, this is what I think, after many corrections, what the result of the subtraction is. So let's go back to LogicSim and check whether it comes to the same conclusion. So this would be known as 88 in hexadecimal. And we'll go back to Logisim, poke the output of the subtractor, and indeed it is 88. Very good. Now this borrow coming out of it is corresponding to, oops, wrong window over here, is corresponding to the overall borrow in our hand calculation. The sign, which is the most significant bit of the difference, is supposed to be a 1. So now we want to find out, how does the ALU get that one single bit as the sign bit. So we switch back to Logisim, and we can see after this wire goes through this multiplexer and coming out of it, we can see how we have a really kind of weird splitter right here. This splitter only splits to get bit 7, which is the most significant bit, and that becomes the sign bit, the sign out. Okay, this tunnel is used later on, but for as far as we know, okay, this is the sign bit. All right, so what else are we getting out of this calculation? What about the overflow, right? So the overflow is taking a look at the most significant bit of the minuend, which is a 0, is taking a look at the most significant bit of the subtrahend, which is 1, and it's also taking a look at the most significant bit of the difference, which is a 1. So we got 0, 1, 1 as a pattern of the most significant bits of the minuend, subtrahend, and the difference. And according to the equation of the overflow, this is one of the 2 conditions to make overflow a 1. Okay, so now we want to know, but how is it done in the ALU? So to see how that is done in the ALU, then what we need to do is to, okay, first of all, we can see how we have S1 and S2 over here. So S1 is really, if you look at the splitter very carefully, it is really just S1 is bit 7, or the most significant bit of in1, and S2 is the most significant bit of in2. In other words, they are basically the sign bits corresponding to in1 and in2. S out, on the other hand, is corresponding to the most significant bit of the difference, because this is where the difference is coming out of the subtractor. Then it goes through the multiplexer in this particular operation. So S out is really the most significant bit of the difference. So we got the minuend, the subtrahend, and also the difference, the most significant bits of those 3 components. So we scroll down a little bit here, and we see this kind of big mess of stuff over here. So instead of looking at the first one, look at the second one. Okay, the second one, which is this one over here. We can see that there are 2 AND gates over here. Okay, let me switch back to a select tool. This is an AND gate. So this AND gate negates the first one and keep the next 2 non-negated. So this particular AND gate is basically negating the sign bit of the minuend and the non-negative version of the sign bit of the subtrahend and the non-negative version of the most significant bit of the difference. Yep, that's our overflow. And this one, on the other hand, is negating, is not negating the most significant bit of the minuend, but it is negating both the most significant bits of the subtrahend and also the difference. This is the one that becomes a 1, okay, and it feeds into an OR gate, and then the OR gate goes into a multiplexer, but this multiplexer shares the same select as OPSEL, or the operation select. So it is also a 001, which means this input is going to this particular output to become our, guess what, overflow. Okay, so overflow is computed inside the ALU using logic gates like this. Woohoo, right? Okay, what about the borrow? Okay, so we look at the borrow bit, which has a tunnel called B, and that tunnel is utilized over here to go through yet another multiplexer selected by the same select bits 001 to become C out. In other words, coming out of the ALU, it doesn't differentiate between a carry or a borrow. Okay, so both addition and subtraction would output their carry or borrow as C out. So what about all of these tunnels? All of these tunnels, except for one of those, so C out becomes bit 0 of flags out. Z out, which is the 0 flag, we'll talk about that later, becomes bit 1. Sign out becomes bit 2. Overflow out becomes bit 3. What about bit 4? What is this? Bit 4 is coming from an exclusive OR gate, and this exclusive OR gate is exclusive ORing the sign and the overflow. This is our L. This is our L flag. Okay, the L flag is the exclusive OR between the sign and the overflow. So now we got all the 5 flags that we want. Now I'm going to go back to talk about what is Z out. So we highlight it first, and we go back and see how it is determined. This is a highlight over here. So Z out is really just the NOR, not the NAND. This is the NOR, negated OR, of all the bits coming out of the multiplexer. In other words, the only one time that Z out is going to be a 1 is when all the input bits are zeros. And that's why it's called a 0 flag, because the 0 flag is a 1 if and only if the result of the ALU is a 0. So now we have all 5 flags inside the ALU. So now we go back to the main circuit and we ask, what is flags out going to? Well, flags out is going to the D port of flags, and this time flags is enabled. Okay, it is enabled. So that means, after I do a Control T at this point, the flags register is going to update. Okay, so let's go ahead and perform the operation, Control T, and we can see how the flags register is now updated to what we saw earlier, which is 0D. And we can also see how the output is now the actual difference. Now that has been the difference already before the Control T, because the ALU itself is actually an asynchronous device. It doesn't need the clock, okay, to do any operation. Whatever inputs that comes in, based on whatever operations being selected, after a propagational delay based on the operation itself, it will update the output. It does not rely on the clock to determine, when should I update the output? Nope, it just takes the input, do the calculation, and instantaneously at that point update the output. The flags register is now determined. Okay, this is the one side effect that, okay, let me go back to the opcode table here. This is the one single side effect that you cannot use in C or C++. You do not have access to the flags after a subtraction in C or C++. Okay, but in assembly we do. Okay, so that's why this operation, which is just subtracting y from x without storing the difference, makes no sense whatsoever in C or C++, but in assembly language programming it is really helpful, because all we really want is to compare. Okay, so now getting back to LogicSim, now we answer the question of why do we care, and if we do care, what is the result of this comparison? So let's go back into the ALU, because I want to look at the individual bits. Okay, so these individual bits are basically saying, if you look at the bit patterns and you look at the unsigned interpretation of the bit patterns, then the answer is yes, because you can see it's light green. So the answer is yes, the minuend is less than the subtrahend. Okay, and that makes sense, because the minuend is 0.8, which is representing the value of 8, and then the subtrahend, which is the bit pattern 80, is representing the value of 128. 8 is less than 128 is true. Okay, so the borrow flag being a 1 is good. That's correct. Okay, what about the signed interpretation? Well, remember, with the sign interpretation, we cannot rely on the sign flag on its own, so we have to rely on the L flag. the L flag being a 0 means that 08, when interpreted as an unsigned value, is not less than 80 when interpreted as an unsigned value. Why? Because 08 is still representing the value of 8 in the signed interpretation, but using the signed interpretation, 80 in hexadecimal is representing the value of negative 128. So when you ask the question, is 8 less than negative 128? The answer is no. So that's why the L flag, which doesn't really have a name because it doesn't have a tunnel in this case, but it does correspond to this 0, which is represented as this 0 as flags out. That's why it is a 0, because 08 is not less than 80 when the bit patterns are interpreted signed. All right. So in other words, we are simultaneously interpreting the values as signed and unsigned. So now the question is, well, if we are getting both of them, then which one do we use to make decisions? Okay, that's the next question, right? That's the obvious next question. So now we are moving on to the jump instructions. I need to look at the time. We got 20 minutes. That I think we got it. So we are looking at the jump instructions, and we'll start with the one that is easier. We'll start with the unconditional branch, which is JMPI. Okay. So once again, the first thing we do is to go back to the opcode table to see how it is represented. So remember, it is not the JMP. Okay. Now JMP with a register has its use, but limited. Okay, we'll get to this one when we talk about subroutines. So we are not quite there yet. So now what we are talking about is JMPI, which is this one over here. So when you look at the C notation of what it does, it looks really awkward. Okay, we are saying that the program counter is updated by the location that the program counter is pointing to in RAM. That's basically what it's saying. Whoa, that is weird, right? When we look at the mnemonics, we also see that JMPI, well, since the instruction ends with an I, we know that it has to use an immediate operand, either as the second one or the only one. Okay, so in this case, it's the only one, the only operand is an immediate operand. So that means whenever we use JMPI, it's going to take up 2 bytes. The first byte is going to have exactly this particular bit pattern, which is 40 in hexadecimal, and then the second byte is the byte that tells us what I really is. Okay, where do we want it to go to? Okay, so the second byte is going to serve as a quote-unquote pointer so that we can tell where we want the program to jump to. So without using the assembler, we are going to just inject that instruction into the processor in LogicSim. So once again, Control R to reset everything, and go to RAM and just inject one single instruction here. So 40 is going to be there regardless, okay, because that's the first byte that's the actual opcode itself, and then the immediate operand of the opcode is the byte that is following it. Okay. So we want to update this to something, maybe specify a 0C over here, okay, because 0C is corresponding to this location, and it would put a 01 over here as a halt instruction. So what I have just specified is a JMPI to location 0C, and then at location 0C, where I'm supposed to jump to, is a halt instruction. So that just kind of stops everything once we get to that point. All right. So now we want to, single transition through this particular program. Okay, so the first thing we do is to look at this part here. So I'm going to spell out, the cycles. Okay, spell out what each transition is doing. So the first one is a rising edge of the clock when the microcode pointer is 000. That's our fetch operation. And I think I typed something else on the keyboard. Control T. There we go. So we can see how the instruction register is now updated to 40. Control T again will increment the microcode pointer without doing anything else. Control T again, the PC or the program counter will increment to location 01. Now this is important, okay? Because without this post increment of the program counter, the program counter would not be pointing to the location where it tells us where we need to go next in the JMPI instruction. So that's why auto incrementing the program counter is really, really important. Okay. The next control T is going to be our decode. In other words, we take whatever is in the instruction register and use it to make, at least part of the microcode pointer. So here's control T again, and we now end up at location 400 in the ROM. So when we analyze the bit pattern coming out of location 400 in the ROM, I'm just going to do the really quick version now because otherwise it will sound really, really boring. We see RAM is being used, so the next question is to ask, are we reading or writing? The LD being a 1 means we are reading. Then we ask who is driving the A port, and we track it down to the multiplexer is taking in input 1, which is coming from the program counter. So the star PC in the opcode table description, the star PC right here, that is now explained. We are using the program counter to specify which location in RAM that we want to access. Now, the next question about the RAM is how we are utilizing the data. We know RAM is driving the D port. In other words, RAM is specifying the content of this particular node. The question is who is consuming it, okay? And we go to this point here, okay? We better make sure that our register output 0 enable is off, because otherwise we end up with a bus fight, because otherwise we end up with a demultiplexer here to also try to drive this particular node if we have both register output 0 enable being a 1 and having register output demultiplexer being a 2. So we can potentially specify a slice of microcode to kill the processor itself, okay? Which is probably not very comforting that the processor actually has a kill switch. Okay, let's see where else it connects to. Okay, it connects to a few things that we are fairly familiar with. It connects to the instruction register, but the instruction register is not enabled. So we know this is not going to be updated. This is the last one. It's going into a multiplexer. The select of the multiplexer is 1, and this is actually input 1. So now we can look at the output of the multiplexer, and it goes into another multiplexer as input. It's input 1 again, and PCMux is a 1. Okay, PCMux is a 1 for a reason, but we'll track it down later. But this is PCMux being a 1 means we are using input 1 as the output of this multiplexer, and it's going into the D port of the program counter. The program counter enable is a 1, so the program counter is going to be updated with whatever is now presented to the D port of the program counter, which is 0C. Okay, this is how we alter the path of execution. Instead of just going for the next instruction and then the next instruction and then the next instruction, now we can say, we want to continue execution at location 0C in the next fetch cycle. This is how we do it, okay? So if I do a control T right now, it's going to update the program counter, but let's check out how PCMux works. PCMux is actually the output of this particular multiplexer here, and to control this multiplexer, which determines the multiplexer of something else, that's why the node or the tunnel name of this particular node is known as PCMuxMux. Okay, it is coming out of the ROM in the processor, and it's 111, which is a 7. So that's why it's taking a constant, which is fed into input 7 of this multiplexer to become the output. And this is why PCMux is a 1. PCMux by itself is not coming straight out of the ROM. PCMuxMux is. But PCMuxMux in this particular case is just connecting a constant of 1 to PCMux, and that is why PCMux is a 1. Alright? Alright, so let's watch the magic happen, which is the next rising edge of the clock right here, Control T, and we can see how the program counter is now. PCMuxMux comes from here. So this is PCMuxMux. which is bit 17 to bit 19 of this particular tunnel. But remember, you have to add 3 to all of these bit numbers. So if you want to look at the ROM, PCMux is corresponding to bit 20 to bit 22. All right. So now we are ready to do another control T, which increments the microcode pointer to location 401. But 401 is going to be 2 followed by a bunch of zeros, which means it's going to reset the microcode pointer back to 0. So here we go, control T, and we can see how it's now going back to location 000, which means we are now ready to fetch the next opcode. So now the question is, where are we getting the next opcode? The program counter says we are going to location 0C to get the next opcode. We have just successfully branched unconditionally from location 00 in RAM to location 0C in RAM. So this is how JMPI works. So are we good so far with the JMPI instruction? Okay. Now I know this is a lot of stuff. You know, there's a lot of stuff here that might take some time to, as they use the term these days, unpack. Okay. So that's why I'm recording the lecture, in the live session, is because if you need to go through this stuff but in a slower way, so that you can actually jot down notes and absorb the material, you can. Okay, this is why we have all of these tools and resources available. All right, so next we're gonna go look at the JCI instruction, okay, which is one of the 5 conditional branches. So we have JCI, JSI. Oops, you cannot see my post-it here. So here's my post-it, and let me put it to a location where the background is not busy. So we have JSI, JCI, JOI, JZI, and then JLI. So what do you notice about the second letter of all of these mnemonics? They correspond to the flags. Yep, they're all flag names. So the only difference between these 5 is which flag do we look at to determine whether we want to branch or not. So once again, the first thing we do, if we want to understand an instruction, we go to the opcode table. So we look up one of those, JCI to be more specific in this case, and we look at the C notation. Now, if you're looking at this C notation and you're asking, what is the question mark and the colon doing in this expression? Then what you need to do is to look up the ternary operator. Okay, the ternary operator is a built-in conditional statement in this form of an expression in C or C++. I don't know how many professors in CISP310 introduces this particular operation or this particular operator. If they don't, they are missing out on quite a bit. Okay, this is a very important operator as far as I'm concerned. So if you're not familiar with this operator, I suggest that you look it up. Okay, ternary operator, and even Wikipedia has a page on it. Okay, so yep, there we go. So the ternary operator, seems to be available in a whole bunch of programming languages, and some of these are prior to C, so it's nothing new. So the way it works, does anyone want me to go over ternary operator just really quickly, or does everybody know it already? Yes, so Richard is correct, and Dan is correct as well. Okay, very good. So I'm just going to go through this in 30 seconds or less. Okay, so we have x question mark y colon z. It is the same thing as saying if x then y else z. Done. How many seconds was that? 5 maybe? Okay, so the longer version is if x is non-zero, then y becomes the value of the entire expression. If x is 0, then z becomes the value of the entire expression. Okay, so it's basically just if then else in a single expression. All right, so let's get this out of the screen. Go back to opcode table. So when you look at this expression here, it's basically saying, let's look at C, okay, the carry flag, and use it to decide which one of these two we should use. If C is true, then it's going to be dereferencing whatever PC has. Oh, that means it's doing the same thing as a JMPI instruction, but only if C is true. You'll be right, okay? That's absolutely true. But what if C is false? If C is false, then we use PC plus 1 to update PC. So that means we are incrementing the program counter again, okay, since the fetch operation. So PC is actually incremented twice compared to what it was right at the moment of the fetch cycle. So that means we are basically just skipping both bytes of the JCI instruction in this case, and just continue on with whatever is right after the JCI instruction. So that's how we perform a conditional branch instruction. So now we look at the opcode, and we'll just do a little quick example to illustrate this. So we look at this. This is a 4-4. Okay, so we go back to the Logisim. Control R, reset everything. Go to RAM and just inject the opcodes. Okay, so we have a 4-4. Whoops. Okay, wrong place because I have to. Now I have to go back to location 0 using edit content. So there we go. We have a 4-4 over here, and let's go to 0C again over here, and then at 0C, this is 0F, E, D, this is C. We put a halt instruction over here. So we are basically using exactly the same program as before, except instead of a JMPI, which is unconditional, now we have 4-4, which is conditional to the C flag, the carry flag. And we have to update. I have to reset just the processor itself because the RAM content is already there, but I just want to reset the processor. So to reset just the processor, here's a reset button that resets everything except for RAM. Okay, that's why I have this button here, because I know that I'm going to do something stupid like what I just did. So now we double check. The program count is once again at location 00, and location 00 is updated. Okay, so we're going to do Control T exactly 4 times so that we get to the slice, okay, that corresponds to the conditional branch instruction. 1, 2, 3, 4. All right, so now we're here, and we want to find out what is going on with this instruction here. We see some similarities between this and the JMPI instruction. We see RAM being selected. We're reading from RAM. The A port is being driven by the program counter, just like before. Okay, so you can see how the address box is a 1, so we are taking input 1, which is coming from the program counter, to drive the address port of RAM. Okay, same as before, no big deal. We look at the output of RAM, and we can see how most things are configured the same way. But this one is not selecting 1 anymore. Why is that the case? Because PCMux is now a 0 instead of 1. But you remember how we determined PCMux previously, right? PCMux is the output of this particular multiplexer, and this particular multiplexer is selected by PCMux. And PCMux this time is no longer 111, which is 7. It is now 000. So we are taking input 0, and basically that becomes our PCMux. And where is that coming from? This is bit 0 of this particular splitter. This splitter connects to the output of the flags register. In other words, we are using bit 0 of the flags register to become the PCMux. Okay, so what is the effect at this point when carry is false? When carry is false, then PCMux is a 0, which means this PCMux is also going to be a 0. If this PCMux is a 0, it's going to take input 0 to feed to the program counter. But this wire or this node connects to the adder, the adder has address mux, as part of the OR gate that feeds into the carry in. So we are really just incrementing the program counter when the carry flag is a 0. Is that okay? So we are not updating the program counter other than just incrementing it so that it skips the byte to specify where we are supposed to go to, if and only if the carry flag is a 1. But since it's a 0, we are not going to that location. We'll just go to whatever instruction is right after the JCI instruction sequentially. Okay? So the next question is, okay, let's go ahead and inject a 1 into bit 0 of the flags register. Just type 0, 1 when it is selected. So now we are now going through the scenario of what if the carry flag is a 1? So if the carry flag is a 1, then the input 0 of this multiplexer is also a 1 because that's coming straight out of the flags register. So that means PC mux is going to be a 1. When PC mux is a 1, then we are encountering exactly the same scenario as when we are dealing with JMPI, the unconditional branch instruction. So PC mux being a 1, going through this kind of strange AND gate feeds into this multiplexer. So now we are selecting this wire to become the output of the same multiplexer, which then goes into a second multiplexer. And PC mux is once again selecting 1, so this is input 1, and it becomes the wire that goes into the D port of the program counter. So now we are updating the program counter based on the data port of RAM, which is already at the location to specify where we are supposed to go to. So that means when the carry flag or whatever flag the instruction should be looking at, if it is a 1, it is basically doing exactly the same thing as a JMPI instruction. But if that flag is a 0, then all it does is to increment the program counter again, so that the program counter will now point to whatever instruction that is after the conditional branch instruction. So that is how a conditional branch instruction works. Do we have any questions? Okay, this is a good time to end the lecture and open the lab for you guys, but I want to make sure that we do not have any lingering questions before I do that. Okay, very good. Oh, we got a question coming. As they say, incoming. Okay. Yeah. So so when you review the material and you guys find a specific question, do not hesitate to ask. I'll stay online at least for the next hour and a half, if not more. So let me go ahead and open up the lab first. Okay. And there we go. Oh, there's one more thing that is kind of important, so I'm gonna have to go through that. So today's lecture is not quite done yet. All right, so the passcode is JXI. Let me write that down first. All right, there we go, and pin it. All right, so that is now pinned, and the due date is, I'll give you guys 1 day to do it. I think you guys can do it in a day. You might have to spend some time to work on this one, but it should be doable in a day. So July 9th, 9 a.m. There we go. All right, so there's one more thing that I really need to go through. It has to do with the operation of Logisim. In one of the questions, it asks you how many times a particular instruction goes through a certain location. So the first thing you need to do is to use the assembler. Okay, and oh, not that one. That's the manual of the assembler, but this is the actual assembler. So you have to use the assembler to find out where that location is based on a label. And the best way to do it is to go to the Assemble tab, which is where I'm already at. So you look up the label definition, like so, and find out what location that is corresponding to using column V to tell you what is the address corresponding to the label where the instruction that I want you to count is located. Okay, so that's one. The other trick that is going to be really helpful is turn on logging in LogicSim. Now, if you want to use the command line logging, that works too. Okay, the command line logging was discussed a long time ago, and some of you, were already using it. But if you don't want to do it that way, there's actually a apparently more user-friendly way to do it. But in the long run, I don't think it is any better. In fact, it is probably worse. But if people want to do it this way, they are welcome to do it. So I'm resetting the processor right here. If you go to the Simulate menu, there's actually an item called Logging. And when you get to Logging, it will ask you what do you want to log. So to answer the question in this particular lab, there are a few things you need to log. The program counter is one that you need to log, and there are two program counters. One is corresponding to the output pin, and the other one is corresponding to the register. You can pick either one because they really are exactly the same thing. Don't pick both, because they're duplicates. Okay, so just pick one of them. I'll just pick the register. Now, once you have picked a particular thing to log, you can change the radix, which is the base. It is by default in base 2. It works okay if you want to look at base 2 numbers all day long. So if you say, I prefer to use base 10, change it to base 10. Or if you say, since the assembler seems to use a lot of hexadecimal numbers, and change it to base 16, that's fine too. So you can choose between any of these three bases. Okay, just pick one. I think most people would use base 10, and some people may pick base 16. They're both good. The program counter is going to be important. The next one, I think the program counter alone may be all that you need. You might also need some of the other ones. I think OP fetch or operation fetch may be useful as well, because that indicates whether we're in a fetch cycle or not. So let's pick that one too. Okay. So once you have selected what you want to track in your log, then you also have some other things to decide. Okay. So I want to change this one to OP fetch is just a single bit. So whether you change the base or not really is not important because it's a single bit. So whether you're choosing base 2, base 10, or base 16, zeros and ones are exactly just zeros and ones. Okay, so it doesn't really matter what base you use for OP fetch. So now you get to choose, do you want to see the log in quote unquote a table like this, or do you want to log the output to a file? If you do not select a file, the default is to use a table. If you select a file, then it goes to a file and the table will not be updated. If you want it to go to a file, you can also include the header line, which tells you which column is corresponding to the program counter and which column is corresponding to OP fetch. Okay, so that's up to you. Okay, if you already remember the order, you don't need it, but if you want to have the file to remind you, then you can go ahead and do it. Discord just complained that I cannot pin the last message, so I'm gonna give it one more try. I think it's because I have an upper limit of only 50 pins for the entire server. Okay, so I'm gonna figure out something over there, but for now we'll just go ahead and focus on this one. Okay, so the one thing that you have to be careful about is if you use file, it would basically append additional logs to the same file unless you do something to reset it. Okay, so this is really important, because if you don't do this, the count that you're going to get is going to be larger than what it should be. Okay, so to know how to use the log file, you can use the user's guide, if I remember correctly. And you click on logging, and we get to the file tab. Okay, so this is rather important, so I need to go through this. Okay, so I'm just going to find the part where it says to reset the file. Okay, I think it's right here. So that a script can process the file at the same time as Logisim is running, Logisim will flush the new record into the disk every 500 milliseconds. Note that Logisim may also intermittently close and reopen. Okay, that doesn't tell me when it refreshes a file. There we go. Okay, it's this portion over here. All right. In the middle is an indicator of what file is being logged to. To change it, use the select button. On selecting a file, file logging will automatically start. If you select a pre-existing file, Logisim will ask whether you want to overwrite the file or append the new entries into the end of the file. So the question now is, if you do not reselect the file and it's already selected as something else, and you basically reset the processor and have it to run a new program, that new program will continue to append to the existing log file, which is not what you want. Okay, so what you really want is one of the two. Okay, so you might want to jot this down, and I'll write it here in the post-it too, so it's actually visual to you. Okay. After running a program, okay, either select a new file of a different name. So I would use jci.txt to log for the JCI instruction, and then use jsi.txt to log the case when the instruction you want to trace is JSI. Okay, or reselect the same file which empties the file first, then start logging. And that's basically how Logisim will do it. Is if you do not do anything about selecting a file, it will continue to use the same file that you have been using already and just append additional entries to that file. All right, so let me illustrate what I mean by this, because I think it's really kind of important for people to understand this part. So let me close all this first, and I go back to logging, and I go to file, and I specify a particular file. So I'll just specify test.log. The extension doesn't really matter to Logisim, but in Windows you might want to name it as test.txt or something like that, because Notepad finds text files a lot faster if it ends with a txt extension. So I click save. It's already enabled, so I close the window. So at this point, I'm going to do a Control K, which just goes through the execution with really fast. So Control K, and it's now done. And then what I'll do is I'm going to use a text editor to show you what it looks like. All right, so here we go. And we'll take a look at test.txt. Nope, I call it log. There we go. So this is the output of the log facility. The program counter is the first column, and then OP fetch is the second column. And you can see that whenever one of these two get updated, it creates a new entry in the program counter in the log file. So in this case, because the carry flag is in fact a 0, so it's not branching to the location 0C. Instead, it continues execution. but all of the other locations in RAM are 0, 0, which is the no-op operation. So the fetch cycle itself has a name, which is the no-op operation, because it just goes to the next available location. So we keep going until we actually get to location C, where the halt instruction is, and that is when the whole thing stops. Okay, so this is one run of the program. So I go back to the processor. Okay, now go back to the processor, and I do so if you want to use a reset, you have to be careful, because when you use a reset, you have to make sure that the clock is a 0 first before you use the reset button of the processor itself. So the clock is its own pin, so the only way to change that state is over here. So if you click it, it goes from, if it's 1 already, it turns it back into a 0. This is when you can click the reset button over here to reset only the processor, but not the program. Now, in your case, you want to reset the entire thing because you will be uploading a whole different program. But in my case, I'm just resetting it like this. And let's just say that this time I am going to change the register bank initially so that we will have the carry flag being a 1, so I can look at the alternate path of execution. So we have 0, 8 and 8, 0. Okay, which should set the borrow flag in this case. So then I don't have to go to simulate again, but I'm going there to show you that it is still using the same file as before. Okay, test.log is still here, and I'm not clicking select now, okay, to show you what happens if you do not reselect the log file. So I close the window. In other words, I didn't do a single thing to reconfigure the logging. So I type Control T again. Okay, and not Control T, but Control K. There we go. So Control K this time gets to location 0F really fast, because this time the conditional branch did happen. So we execute the JCI instruction and it went right to the halt instruction. So Control K one more time to disable the clocking. So now when we look at the log file, it should be what? It should be a longer version than what it was, because it did not reset the content of the log file. So this is the log file before I reran the Logisim, and you can see the last line currently is line 38. If I update the file, okay, if I do an exclamation point in VI, it updates the file. It updates the editor to the current content of the file. And you can see how now it has these additional entries. Actually, it did not go through the conditional branch. Oh, that's because I changed the register before or after I reset the processor. I might have reversed those two operations, but the key point here is it just appends additional stuff into the log file, which is not what you want it to do. Okay, so what you want to do is, before you start the next logging session, okay, is to go to simulate, go to logging again, and either select a different file, which is what I would strongly suggest, is to select a different file. Okay, so if JCI is the one that you're logging at the point, change the name of the file to JCI. If JSI is what you're logging at that time, change it to JSI. So you will use 5 different files, one for each instruction. That will basically prevent all kinds of confusion. Now, if you do it like this and start logging again, and I'm resetting the processor and go to the register bank. Yeah, so I think last time I reversed the process. I set the content of the registers and then I reset the processor, which also resets the registers. Okay, and now I can do a Control T to clock that single clock, Control K to clock automatically. And this time, when I stop processing, I now have a new file called jci.log, and this is jci.log, which also does not branch directly to location 0C. Well, I have to kind of figure out why that is the case, but it did not branch directly to um, location 0C, but it is a new file. It starts from the beginning. That's the important part. And one more thing, if you use the command line version, to track down, to generate the trace, which is actually a better way to do this. If you do it that way, then when you look at a question, you have to do one more thing. So when you look at a question and you want to use the command line method to do the tracing, you have to remember that you have to start with a no op operation at the beginning. So let me go over to here. So if you use the CLI method to do the logging, just put a no op right before the LDI instruction. That's what you need to do in order to use the command line version correctly. And then we can use the trace analyzer, which I haven't really talked about yet. So we'll just kind of assume that you guys are going to use the log facility that is built into Logisim. So I'm done for today's lecture, and let me see if there are any questions. That's a good question. When did I talk about the command line logging? Let's not do it with this lab, because to do it with this lab using the command line logging, you will also need to use the trace analyzer. So those are some kind of additional tools that that may be a little bit overwhelming when you already have to do the homework assignment. So we can talk about that maybe sometime tomorrow, but not today. All right, so unless there are some additional questions, I'm going to be off of the live stream for now, and then I'll be back in about 10 minutes to answer questions.